Welcome back to Physics 191. I'm Gerard Blanchard. We're going to continue this time with Newton's second law, applying Newton's second law to situations. If you remember, Newton's second law is what we apply when we have non-equilibrium situations. Non-equilibrium meaning we don't have static or dynamic equilibrium. And in that case, the object accelerates, and the acceleration of that object is equal to the total force acting on that object divided by its mass, and those are vectors, of course. Let's go to another exercise to help you practice with this. A crate of books is to be put on a truck by rolling it up an incline of angle 15 degrees using a dolly. The total mass of the crate and the dolly is 25 kilograms. Assume that rolling the dolly up the incline is the same as sliding it up a frictionless surface. In order to start the dolly moving, it must be accelerated from rest. So what horizontal force must be applied to give the crate an acceleration up the incline of magnitude 0.5 meters per second squared? Now, remember, the first thing we do is we draw a diagram and list our knowns and unknowns. The word acceleration is a hint that this is a non-equilibrium situation. And also note that it asks you what horizontal force must be applied. So that means that the applied force in this case is going to be horizontal. So make sure that you draw it that way. Please try. Please draw your diagram, list your knowns and unknowns, and get started. Okay, we start by drawing a diagram. I'll draw the ramp. Here's our ramp, and here's our crate on the ramp. We are told that the ramp makes an angle of 15 degrees with the horizontal, and that the crate has a mass of 25 kilograms. Well, if the crate has a mass of 25 kilograms, we can figure out its weight. Its weight is going to be vertically downward, and the magnitude of weight is its mass times g, or the weight is equal to 25 kilograms times 9.8 newtons per kilogram, or the weight is equal to 25 kilograms times 9.8 newtons per kilogram. That would be 245 newtons. Okay. What other forces are acting on the box? Well, we're told that rolling the dolly up the incline is the same as sliding it up a frictionless surface, so I won't be drawing in friction. We are told that there is a horizontal applied force, so I will draw in a horizontal applied force that is causing the box to accelerate up the incline. So force applied, and we're asked what is the magnitude of that applied force. So that is what we're looking for. That is our unknown that we're looking for. And this horizontal force gives the box an acceleration up the incline with a magnitude of 0.5 meters per second squared. Okay. And what else? Well, that's everything that we're explicitly given in the question statement. Now, there is one thing that we can infer from the question statement, and that there is a normal force perpendicular to the incline. Even though there's no friction force between the box and the incline, the box is still feeling a force from the incline that is perpendicular to the ramp. And that's what keeps the box from falling through the ramp. So I'll draw in the normal force perpendicular to the incline. So it'll be in that direction. And now I have indeed drawn in all of the forces on the box. That is everything that we can get directly from the question statement. That's all of our forces, our acceleration, our diagram. It's time to draw some coordinate axes. Well, to do that, I would advise rotating the page so that the ramp becomes horizontal. That also gives us the benefit of making the acceleration horizontal. And making the ramp our x-axis, and y would then be perpendicular to the ramp in that direction. So now, if we take a look at our vectors, the acceleration is completely in the x direction. The normal force is completely in the y direction, but our weight and our applied force are now neither completely in the x or completely in the y, so we're going to have to break them up into x parts and y parts. Let's start with the weight. Weight, as I've rotated it, is now down and to the left. So I'm going to break that up into left and down. Okay, so weight, which is to the left and down, I can represent as a right triangle. Here's my right angle right here, where one side is to the left and one side is down. We have to figure out an angle in this triangle, and I'll use this angle right here. Okay, and the reason why I'm doing that is because I'll rotate back really quickly. You can see that I have a right triangle right here. This is a right angle. So this makes a right triangle, the ramp, the horizontal, and weight. So if this is a 15-degree angle, I know that this angle is going to be 90 degrees minus 15, or this angle in here is going to be 75 degrees. So that angle right in here is a 75-degree angle. Okay, now let me rotate back. Okay, now that we have this 75-degree angle, this side is going to be opposite the 75-degree angle. So this side is going to be weight opposite, and this side right here is going to be weight adjacent. Weight adjacent is in there. Okay, and I have to do the same thing for the applied force. As I've rotated the diagram, the applied force is down and to the right, so I'm going to have to break that up into a right triangle that is down and to the right. And I need an angle. I'm going to pick this angle right here. And the reason is because this line right here represents my original horizontal, and this line represents my original horizontal. So these are parallel lines. This side of the force triangle and the ramp are also parallel lines. So I have two sets of parallel lines, which means if this is a 15-degree angle, then this in here also has to be a 15-degree angle. That comes from geometry. So when you have two sets of parallel lines crossing each other, the interior angles will be the same. So I know that this angle in here is a 15-degree angle. And that makes this side force applied opposite to the 15-degree angle, and force applied adjacent is right there. So this is my applied force. This is force applied opposite, force applied adjacent. Here's my weight. This is weight adjacent to this angle and weight opposite to this angle. So we've drawn our diagram, listed all of our knowns and unknowns, drawn in our forces, drawn in our coordinate axes. Now our diagram is complete. And I'll rotate back now. Now that we've done everything that we can get from the question statement and everything that we can infer from the question statement, we need to start using some physics. We need to bring some physics into this now. And since the box is accelerating in the x direction, our appropriate starting equation would be the appropriate starting equation for x non-equilibrium, which is the ax, the acceleration in the x direction, is equal to the total force total in the x direction divided by the mass of the box. In the y direction, we have equilibrium, because as the box accelerates up the ramp, it's not moving in the y direction. It's not moving perpendicular to the ramp. So the box is not moving in y, as I've drawn my y-axis, and it stays not moving in y. So we have y equilibrium. And our starting equation for y equilibrium is force total y equals 0. Let's see what we can do with these equations. Ax, the amount of the acceleration in the x direction, well, that is 0.5 meters per second squared. The box is accelerating up the ramp at 0.5 meters per second squared. The x-axis is up the ramp. That means that the acceleration in the x direction is positive 0.5 meters per second squared, because the acceleration is in the positive x direction. Now that is equal to the total force in the x direction. What forces do we have in the x direction? Well, normal force is not at all in the x direction. It's completely in the y direction. So normal force won't appear in this equation. The applied force is partially in the x direction. The adjacent side of force applied, the side adjacent to this angle, is in the positive x direction. So that would be plus F, force applied, adjacent. Now, weight has a component that is in the negative x direction, or down the ramp, and that is this side of the weight triangle. And so that would be weight adjacent. But it's in the negative x direction, so that would be minus weight adjacent. And those are all of our forces in the x direction. So that, which I've written here in parentheses, is F total x. And we'll divide by the mass. The mass of the box is 25 kilograms. Okay, let's expand that a little bit. That would be 0.5 is equal to force applied adjacent. So that is this side of the force applied triangle. The adjacent side would be, this side would be force applied, whatever it is. We don't know what it is, but it would be force applied times the cosine of this angle. So force applied times cosine of 15 degrees minus weight adjacent, minus this part of the weight triangle. So that would be the weight, which is 245, times the cosine of this angle. So remember that the adjacent side is always cosine. The side adjacent to the angle is hypotenuse times the cosine of the angle. So 245 cosine of 75 degrees in this case. All of that divided by 25. And what you can see here is that we now have an equation with one unknown in it, which is force applied, which is what we're looking for. So all we have to do is to solve this equation for force applied. How do we do that? Well, I can multiply both sides of this equation by 25. So it would be 0.5 times 25, and this side of the equation times 25 just leaves me with FA cosine of 15 degrees minus 245 times cosine of 75 degrees. Now I can add 245 cosine of 75 degrees to both sides, and that is 0.5 times 25 plus 245 cosine of 75 degrees, is equal to force adjacent times cosine of 15 degrees. And I'll put parentheses around this, and then divide both sides of the equation by cosine of 15 degrees. And that gives us 0.5 times 25 plus 245 times cosine of 75 degrees, all divided by cosine of 15 degrees equals force applied. And now we can calculate what force applied is. So that would be 0.5 times 25 plus 245 times cosine of 75 degrees, parentheses, divided by cosine of 15, and that gives us 78.6 newtons. So 78.6 newtons is equal to force applied. And this answers the question that we were asked for. So that is the answer. What horizontal force is necessary to give the box an acceleration of 0.5 meters per second up the incline? The answer is a horizontal force of 78.6 newtons. So how do we do that? Let's review. We started by modeling the system. Now, what does it mean to model the system? We drew in our diagram with our forces. We chose our X and Y axes. We broke down the forces that were not aligned with the axes into triangles. And all of this is our essential first step, to draw our diagram with our forces. We then applied the relevant basic physics. And in this case, our relevant basic physics are that we have non-equilibrium in the x direction and equilibrium in the y direction. Non-equilibrium in the x direction gave us our starting equation of the acceleration in the x direction is the total force in the x direction divided by mass. And by working that, we worked it down to the answer. We also, in the y direction, we had the equation that the total force in the y direction is equal to 0. We turned out not to need that, but we could have. We didn't know ahead of time that we wouldn't need this equation, but as it turns out, to answer this question, we didn't. let's do another exercise. In the figure, two blocks are connected by a lightweight, flexible cord that passes over a frictionless pulley. If mass 1 is 3 kilograms and mass 2 is 5 kilograms, what are the accelerations of each block, and what is the tension in the cord? Now there's two things that we have to realize here before we even get started. Well, we could introduce them later, but I'd like you to realize two things here. One is that since the blocks are tied together, the magnitude of their accelerations has to be the same. If one is accelerating at 1 meter per second squared, then the other also must be accelerating at 1 meter per second squared. Maybe in a different direction, but the magnitude of the two accelerations have to be the same. The other is that the tension in the rope is the same on either end. So the acceleration of the blocks is the same and the tension is the same. Now, one more thing to realize is that if we're treating these two blocks as two different objects, and we should be, then we can write an equation for each of them. We can actually write an x equation for each and a y equation for each. As it turns out, we'll only need the y equations, so we can write a separate y equation for each. A separate acceleration in the y direction is equal to total force in the y direction divided by mass. So, draw your diagram, list your knowns and unknowns, think about what I asked you to think about, and please get started on this exercise. Okay, let's draw our diagram. We have two objects. We have mass 1, and we were told that that's 3 kilograms. And we have mass 2, and that is 5 kilograms. And I'm not going to draw the rope. Well, I'll draw in the rope actually. I'll draw in the rope, but I'm not going to draw in the pulley because we're really concentrating on the two masses. So we only have to draw the objects that we're going to apply our equations to. So in this case, that's the two masses. So I'm only going to draw the two masses. I have to draw in the forces on the two masses. Well, in both cases, tension, T, is pulling up on both of them. And it's the same tension, so I'm just going to use one T. I'm not going to write T1 and T2. Same tension, one symbol for it. So T. We have to think of other forces acting on these two masses. Well, weight. And that's it. Weight. So we have, I have to write weight 1 is equal to mass 1 times G. Weight 1 is equal to 3 times 9.8, weight 1, and I'll come back to that. Weight 2 is equal to mass 2 times G. Weight 2 is equal to 5 times 9.8, or weight 2 is equal to, grab our calculator, and 3 times 9.8 is equal to 29.4. And 5 times 9.8 is equal to 49.0 newtons in both cases. So we've drawn in all the forces. We've drawn in our unknowns. Our tension is our unknown. Same for both. And we should indicate the acceleration. Well, if we have 5 kilograms on this side and 3 kilograms on that side, we can expect that this one will accelerate downwards, and I'll write I'll draw in A2 being downwards, A1 being upwards, and I did say that whatever the acceleration of 2 will be, whatever the magnitude of the acceleration of block 2 is, block 1 must have the same acceleration, same magnitude acceleration, different directions. So I'm just going to rewrite that as A, that's an unknown, and A1 is equal to the same A, which is an unknown. And at this point, we have drawn everything that was, and written in everything that was in our problem statement. So all we've done is we've taken the statement that we were given and we've modeled it with this diagram. Next step is to draw in, next step is to draw in our coordinate axes. And I'll draw in Y and X. And as you can probably see, X is unimportant here. All the motion, all the forces are in the Y direction, so we don't have to worry about X in this case. The next step is to write out our starting equation, to identify the situation, write out our starting equation. And since these objects are accelerating, we have a non-equilibrium situation. So object 1 is Y non-equilibrium, and object 2 is Y non-equilibrium. And so we'll write out the same equation for both of them, but with the subscript 1 and a subscript 2 wherever it's appropriate. So that would be the acceleration in the Y direction of block 1 is equal to the total force in the Y direction on block 1 divided by mass 1, and acceleration Y2 is equal to the total force in the Y direction on block 2 divided by mass 2. Okay, that's our starting equations. The next step is to make these equations specific to this situation and to work through it. And I can guarantee you the answer is in there somewhere. You might not see it at this point. It actually takes a lot of experience to be able to see how the answer is going to come out of these equations. Well, experience, you're getting experience now by working through this. You'll have homework, and with time, you'll be able to see where the answer comes from. Right now, I guarantee the answer is in there somewhere. So keep working and see if you can get the answer. If not, don't worry. Don't worry about making mistakes. As I always say, mistakes are where you learn, and I will reiterate that often. Well, let's see. The acceleration of block 1 in the Y direction is positive. Block 1 is accelerating upwards, or we assume, and it's accelerating with an acceleration of A. That is equal to the total force in the Y direction, the upward forces minus the downward forces. The upward force is T minus its weight. So actually I'll go ahead and write weight 1 divided by mass 1. For block 2 is accelerating downwards, we assume. So we have minus A is equal to tension minus weight 2 over mass 2. Now, if we assume incorrectly about the direction of the acceleration, that's okay. What will happen in the end is we would get a negative sign for A. So you can make these assumptions and you'll know that they're right when you get a positive number, or that they were wrong when you get a negative number. Carrying on, we have acceleration is equal to tension minus weight 1. Weight 1 was 29.4 newtons divided by mass 1 of 3 kilograms. And for the other equation, we have acceleration is equal to tension minus weight 2. Tension minus 49.0 divided by 5 kilograms of mass. And as you can see here, what we have is we have two equations in two unknowns. And that's okay, we can solve that. What we'll do is I'm going to solve both of these equations for tension. And then they'll be equal to each other, so I can set them both equal to each other. So carrying on, we have multiplying both sides by 3 over here. We have 3a is equal to t minus 29.4. And over here, we have minus 5a is equal to t minus 49. And then adding 29.4 to both sides, I have 3a plus 29.4 is equal to t. And I have minus 5a plus 49 is equal to t. So now I have two things that are equal to t. Well, if they're both equal to t, then they're equal to each other. So I can write 3a plus 29.4 is equal to minus 5a plus 49. And I have an equation with only a in it. What do? Well, I'll add 5a to both sides, and I'll subtract 29.4 from both sides. And I'll have 3a plus 5a is equal to 49 minus 29.4. I'll rewrite what we have so far. We have 3a plus 5a is equal to 49 minus 29.4, or 8a is equal to 49 minus 29.4, or dividing by 8, we have a is equal to 49 minus 29.4 divided by 8. Or acceleration is equal to 49 minus 29.4 divided by 8, or we have an acceleration of 2.45 meters per second squared. So we've answered half of the question. Acceleration is 2.45 meters per second squared. The other question was, what is the tension? Well, I can go back to either one of our equations that we had earlier. In this case, I'll take 3a plus 29.4 is equal to tension. Should recognize that equation from above. And now I have a. So 3 times 2.45 plus 29.4 is equal to t. Three times 2.45 plus 29.4 is equal to 36.8 equals t. And we know that our units, since t is a force, our units must be newtons. So 36.8 newtons is equal to the tension. And we've answered both of the questions we were asked. The acceleration is 2.45 meters per second squared, and the tension is equal to 36.8 newtons. Now I will mention, as you're working this out, if you are videotaping or if you're watching this on the computer, you can always pause and try to stay ahead of where I am. It's a very good practice for you to work these out ahead of me so that if you make mistakes, you'll learn from them. Don't be afraid to make mistakes. It's a learning experience, and that's what we're here for. We're here for you to develop a skill, the skill of doing many things, visualizing what you're told in the exercise statement, to visualize forces that must be there, even though you might not recognize them at first. You will certainly learn to recognize the normal force whenever you have an object sitting on a table or on a ramp. You know that there must be a normal force. Recognizing when there's friction, recognizing Newton's third law force pairs, such as the horse pushing on the ground that we had earlier and the ground pushing on the horse. These are all skills that we're working to develop, and they're skills that you develop through practice. So trying to stay ahead of me is very good practice. Now we know how to find acceleration when we're given forces. That's Newton's second law. The acceleration of an object is equal to the total force on the object divided by its mass. But why? Why are we concerned with acceleration? Well, as it turns out, what acceleration means is a change in velocity. So that's what we're interested in. We're interested in how objects change their velocity. And they change their velocity over time according to their acceleration. There's an equation for that, as you might expect. And the equation is that if acceleration is constant, so for an acceleration that doesn't change in time, then we can write out the equation that the acceleration vector is equal to the change in the velocity vector divided by the change in time. Now the word change, or the idea of change, is symbolized in this equation by a Greek letter delta. That's a capital delta. It looks like a triangle. So we have a change in velocity in the numerator and a change in time in the denominator. Now this equation is actually a definition. This is the definition of acceleration. Acceleration is defined to be the change in velocity over the change in time. Now both acceleration and velocity are vectors, so this is actually a vector equation. Vector acceleration equals, or is defined to be, the change in the velocity vector divided by the change in time. Since it's a vector equation, that's equal to two component equations, an x equation and a y equation. Let's take a look at the x equation. The x equation is the acceleration in the x direction, or a sub x, is equal to the change in the x component of velocity, or the change in v sub x, divided by the change in time. Now time is not a vector quantity. Time is a scalar quantity, and it's going to be the same delta t in both the x and y equations. There's no x component of time or no y component of time. Time has no direction in space. So expanding that out a little bit, let's get rid of that delta and let's get to what we really mean by change. And we have acceleration in the x direction is equal to the final velocity in the x direction, or v sub x final, meaning at the end of our interval, at the final velocity is the velocity at the final time. For when we're dealing with velocity and velocity changing over time, our situations will always define a starting time and a stopping time. We'll always be dealing with a time interval. So time initial starts the time interval, time final stops the time interval. And so we'll use an F and an I to indicate the final time and the initial time, or the final velocity and the initial velocity. So we have acceleration in the x direction is equal to Vx final minus Vx initial. So final minus initial, that's the change. That's how much the velocity, at least the x component velocity, has changed in that time interval. And we divide by the change in time, which is time final minus time initial. Similarly for y, the acceleration in the y direction is the change in the y component of the velocity divided by the change in time, and that's equal to the final y velocity minus the initial y velocity, all divided by final time minus initial time. Now, I'll make a note here, and that is, I said above that if acceleration is constant, then we have that equation. If the acceleration is not constant, then strictly speaking, it is the average acceleration that's equal to the change in velocity over change in time, or a vector average is equal to change in velocity over change in time. But for the purpose of this course, the acceleration will always be constant, or at least piecewise constant, and I'll explain what I mean by piecewise constant later on when we encounter a situation that requires it. But acceleration will always be constant for the time intervals that we consider. So in other words, we can always choose a time interval where the acceleration is constant. So, but I do mention that average acceleration because some of your exercise statements will ask you what is the average acceleration. Well, they mean acceleration as we're talking about it. Let's talk about velocity for a second. Velocity, as I said, is a vector. The magnitude of velocity is speed. It is the meters that you're moving per second. That is the magnitude of the velocity. Speed doesn't say what direction you're moving in. The speedometer of your car, for example, only tells you how fast you're moving, not which direction you're going. And you can travel at constant speed and change direction. So speed is not velocity. Speed is the magnitude of velocity. Velocity is speed and direction. The speed is related, being the magnitude of the velocity, the speed is related to the x and y components of velocity by the Pythagorean theorem. Or in other words, speed is equal to the square root of the x component of velocity squared plus the y component of velocity squared. However, both speed and velocity have the same units, meters per second. Speed and velocity do tell you the number of meters that you're moving per second. You may be more familiar with miles per hour, kilometers per hour, but in all of those cases, it's still just a distance unit over a time unit. And in Physics 191, we would always convert those to basic metric units. So if you know your speed in miles per hour, then you would convert miles to meters and hours to seconds to get your speed or your velocity in meters per second. Now that we know about acceleration and velocity and the relationship between them, we can define a new type of situation. This is our third type of situation. It's going to have another starting equation. This type of situation we'll call a kinematic situation. That comes from the Greek word for moving, a moving situation. So how do we identify a kinematic or moving situation? It's a situation that deals with either acceleration or velocity or position. We haven't talked about position yet, but you'll see that position also involves kinematics, or kinematics also involves position, and time. When we're dealing with acceleration, velocity, position, and time, we have a kinematic situation. The fact that these quantities are changing in time is our hint that we're dealing with a kinematic situation. So what is our starting equation? Actually, we're going to have 4 starting equations for kinematic situations. The one that we've just encountered is our first starting equation of 4. First of 4, our first starting equation is that the acceleration of an object is equal to the change in its velocity divided by the change in time. Or, once again, being a vector equation, we have an x and a y component, or the x component of acceleration is equal to vx final minus vx initial divided by T final minus T initial, and AY is equal to VY final minus VY initial over T final minus T initial. And note that a situation can be both equilibrium and or non-equilibrium and kinematic. So now we have more equations that we can bring together to solve for more unknowns in a situation. So whatever the situation is, we may have to bring in our kinematic equations, our equilibrium equations, and possibly our non-equilibrium equations. But the answer will be in there somewhere. We're going to do some examples of some kinematic situations in our next episode. Until then, think physics.